today we will continue the LVDT based position transmitter design and then see totality how this position transmitter looks like. So far we have discussed about LVDT excitation, that is we have shown how to excite the LVDT using sine wave, Then we have discussed about temperature compensation for LVDT, Then we have discussed about V1 minus V2 is proportional to displacement, and then how to convert V1 minus V2 is converted into proportional current, So today we add the power supply to this, and then that becomes a complete two-wire system for LVDT. So first I show what we have done up to now without involving the power supply, then I add the power supply. So what is done so far is that we had the LVDT here, primary of the LVDT, and then we had the secondaries, two secondaries there. Then we had the rectifiers here, and then to this center tap we had put the voltage lifting up using a Zener diode. We had done this. Then this voltage actually rectified and filtered. So this is taken as V1 and V2, and then this actually V1 plus V2 was added up. So what we had done was we had added up plus minus, in the minus input we had added up these two voltages. Then this is given to V reference, and this was fed back. This is fed back to the oscillator circuit. Oscillator circuit consists of Hartley oscillator. Essentially you had the inductor, transformer for Hartley oscillator. So you had energized this one, and this was fed to this, the DC voltage fed to the oscillator, and then you had the secondary, and the resonating capacitor has been put, and then this was connected to that, and these are biasing resistors. So this is again connected to the supply of the input supply to this. So essentially the core actually moves here. So essentially this voltage is fixed. So if if they take the LVDT, and then if the LVDT core moves, then we know that V1 and V2 will change, and then we are adding this and finding V1 plus V2 here and comparing it with the reference. If V1 plus V2 it goes more than the reference, then the output voltage comes down. That reduces this voltage, that reduces the amplitude of the oscillation, and that makes again V1 and V2 to come down to make it V1 plus V2 always equal to VR. So by this arrangement we had made V1 plus V2 always constant, and then now we have taken V1 and V2, the difference between these two should be used to drive the current. That we have done like this. So we have taken V1 here and V2. If necessary, this can be even voltage follower can be put here to remove. So I can add the voltage follower here, so that this voltage will not create any voltage drop due to the. So, I can add a regulator, the voltage follower here. So, now this becomes V1 and V2. This was used to convert into current. So, we had fed this one to the current converter here. So, the current converter was made like this. And this is the power supply point. Of course, this is to be biased to the, also to the power supply V. So, this is connected to V. You have this also connected to V, and then we had this input voltage to V2, and then to offset the voltage we had done this is given to V reference and then connected to this. So, this is connected to V1 and the other input is connected to V2. So, you have V2 here and then V2 here and then it has been. So, V1 can be connected from here. So, you have V1 here, V2 here, and the difference drives the current through this. So, this current I is proportional to displacement eventually, and that can be made 4 to 20 milliampere by suitably adjusting this, and even the span adjustment can be given here using a potentiometer. And then now we have to add the regulator for this to make it a two-wire system. So, what you do is that we have to provide a regulated supply. This we already discussed in the earlier current transmitter design, but nevertheless we can do it again, that you can have this and then put the regulator at this point. So, what can be done is we can have a follower here and then the error amplifier can be added at this point. The error amplifier actually sees the output. We also explained about this using the zener. The voltage can be boosted out here, and this supply is connected to this, and then this minus and plus, and we have the divider arrangement here, and the plus can have a reference voltage like this. That regulator output can be given to this. So, you will have the input connected here and the output to the ground. So, eventually that this gives you fixed regulated voltage 8 volt, and the entire circuit works on 8 volt, and then the amplitude of the LVDT is stabilized such that V1 plus V2, that you have the V2 here at this point, V1 plus V2 is kept constant, and then V1 minus V2 gives you the displacement. So, that gives you the full circuit of this. So, what is done is when input is regulated using this op amp, that is op amp 1. So, op amp 1 used to regulate the input voltage and gives the regulated voltage. Op amp 2 is actually makes V1 plus V2 constant, and then this operation amplifier 3, this operation amplifier 3 converts V1 minus V2 difference into current. So, the op amp 1 is a voltage regulator, op amp 2 makes V1 plus V2 constant. Then that is op amp 2. Op amp 1 does this, op amp 2. So the op amp 2 makes V1 plus V2 constant. V2 constant. Then op amp 3 makes V1 minus V2 proportional to I. So that way the displacement eventually convert into current variation as the core moves, then this current as the core moves here, and this current varies, that is the eventual net result. And we had shown how to bias this one to avoid the temperature drift, that we had explained in the previous class using this, because this diode and this diode are matched, so that temperature drift is compensated in the circuit. So this op amp and this op amp are only used as a voltage follower to avoid the loading, and this transistor is used to produce oscillations in the circuit. So this is how the current transmitter design works. We can now see the reverse of this current transmitter, because now we had seen in how to use LVDT as and then how to construct a current transmitter. Now in the industry what they do is they also send a current and expect us to convert into a signal, and then also use the same current to power the device. So what is normally done is, like we have a current for example, if I have a current source, constant current source, this constant current source is transmitted over a long distance, and at the receiving end we will have an instrument. That instrument should produce output voltage, that mostly it is with respect to this ground, this produces output voltage. This voltage will be constant, this V0 has to be constant, is V0 should be kept constant. Even this current varies, this current normally varies from 4 to 20 milliampere. So this is a 4 to 20 milliampere current transmitter, and even this current varies, this voltage should be kept constant. That is one requirement. The second one is the current that is flowing through this is sensed invariably using a resistance, and this voltage, this voltage is actually V input, that is, or V signal we call. So this V signal gives you the current information. If the current is 4 milliampere, you will get some voltage. If the current is 20 milliampere, you will get some other voltage. So this voltage will be used to activate various signal. This signal is used to activate the control valve according to this current. If the current is 20 milliampere, then the valve will be moved fully. The current is 4 milliampere, the valve will be shut down. And for that operation we need a electronic circuit. Power for that electronic circuit should come from this V0. So eventually it looks like this, that this voltage will be used to power the circuit, and this will be used as a signal to activate the actuator or anything else. So this is actually the conversion of current to splitting the voltage, splitting the current, splitting the current into signal and power. This is another application which is extensively used in the process control industry. So we see how that can be done, because before doing that we have to understand what is the current source, how the current source is useful. We are already discussed, if we use a current source, that the noise pickup is low. So, now we explain what is the current source, and then what is the property of that, so that we can design this converter which converts current into signal and power. So, basically we already discussed about once the current source. So, if you look at the constant current source, for example, a typical constant current source looks like this. This is a load, and this is a supply V plus, say 15 volt we are given here, and the ground is given here, and this is the load. So, if you find the current through this is actually given by V Z by R, that V is a ZNR voltage. For example, if I put 5 volts ZNR here and if I put 100 ohms here, then the current I would be 5 volt divided by 100 ohms, that will be 50 milliampere current. So, this is a constant current source of 50 milliampere. That is this actually the current flowing through this is always constant, given by this, given by this, and it is independent of this resistance value. Even if I change this resistance value, the current will not change, that will be always constant. That is the exact meaning of the constant current source. We will also be discussing more about this little later. Now, let us see how we can do this. Now, if I use this current source, I transmit this for long distance, and I want to convert this current into signal and the power, because the same current source should power the remote device, and also the current information also to be carried taken, and that should be used to control the valve, etc. So, normally what is done is, for example, I remove this load. Now, what I do is I will just convert this, I transmit this for a long distance, then I have a load here, and then bring back to the ground. Now, this current will vary if I vary this resistance. Now, to convert this into power, what I do is, whatever current that is coming from the long distance, I want to convert into first a power, that is I convert into a constant voltage. So, for that what I do, I will put a capacitor here. So, if we look at this current transmitter, that you have this, the constant current is coming and that is grounded. If I put a capacitor here, whatever current that is coming here will be charging this capacitor continuously, and the voltage across this will be continuously be increasing. Now, how much voltage it will reach? Eventually it will reach 15 volt, because this is this constant current source is driven through a 15 volt supply here. So, it cannot go beyond 15 volt. So, this will go 15 volt eventually, whatever may be the current here. Now, I have to use this for powering the various devices. So, if I connect this to a resistance here, and if this resistance changes, then what will happen is, depending upon this load, the voltage across this will be varying, because if the load resistance is small, then you will find most of the current is going here, and then as the voltage and then only small current is going, even that as the time passes the voltage will increase, and then more current will flow across this. So, eventually voltage across this is given by this resistance and the current. So, what actually happens is, the V0 here what you get would be V0 by R, that would be input current I. So, if this is current I, then if the voltage at this point is determined by the R, in fact if I varies, if this current, this current can vary 4 to 20 milliampere. So if this I varies, eventually you will find this V0 also changes. Similarly, if R changes also, the V0 will change, but we do not want this to happen. We want V0 to be constant irrespective of this current and irrespective of this resistance change. So how to get that? So that we can do it in the following manner. What I do is, I will take now this current source, take this current source. Now I put the capacitor here, then I connect the operation amplifier here, and then I power the operation amplifier also there, and to avoid the capacitor being discharged, I put on a diode so that the current cannot go back. So I power this operation amplifier using this. Then I take the output of the operation amplifier. I have the two inputs. Now the output of the operation amplifier I connect to a transistor, which is again connected to this. It is biased using these two resistors. I will explain more about this shortly. Then I will connect this through a small resistance, connect to the collector. So what happens is, if this voltage is if the voltage at this point is more, then the transistor will conduct more and more current will flow through this. So if more current flows through this, then the voltage across the capacitor will decrease. Similarly, if this voltage is low, then this transistor will conduct lightly and less current will flow. The less current flows, the voltage will increase. That means if more voltage here, then you will find less voltage at this point. If the voltage is less here, then you will find more voltage here. So this to maintain this at constant voltage, we have to configure this comparator correctly. So this I can do one thing, that I can connect this to output sensing. So I connect this to the output, then this I connect to the reference voltage. So this is this point is sitting at V reference, say 5 volt. This is 5 volt. So this is sitting at V reference. Then if I take, for example, equal values for this 100k, then if this has to be 5, if this has to be because if this is sitting at 5 volt, this also have to sit at 5 volt. There is no other go. Suppose if this is 5 and the less than 5. If it is less than 5, then output will go high, then this will conduct more, then this voltage will come down. And in fact, if this voltage comes down too much, then this will come below 5. If it comes below 5 and if this is 5, then output will go high, then it will conduct more and this voltage will decrease. If it goes, actually I have to reverse the thing. If it goes lower, it is so this polarity is to be reversed. So what I do is, I will change this polarity, then it comes all right. So you put this one to plus, this one to minus. So if the voltage is if this voltage is at 5 and if this is less than 5, if the less than 5, then output will decrease here, because this is 5 and this is lower than 5. So output will decrease, that will make low current here, and that will increase this voltage. And if this voltage increases, and if it goes more than 5, then output will go high and the more current will go and this will reduce. So eventually, by this mechanism, if I keep this one at 5, this will also remain at 5, and since these two resistors are equal and the current flowing through this is negligible, so voltage at this point is 5, means this has to be 10, because the voltage across this and this has to be same, and voltage across this 5 and this is another 5, so you will get 10 volt. So in fact, you can adjust this resistance to get whatever voltage that you want. But now whatever may be the case, that voltage at this point will be always at 10 volt. So by this process, we have now regulated the voltage to get 10 volt. Now we can add whatever load that we want to here. So this is the actual load. If the load is taking more current, then if the load is taking more current through this, then what really happens is, if the voltage, if the load is more, the more current flows through this, then the regulator reduces the current that is flowing through this, because if the voltage decreases because of more current, then automatically this voltage will decrease and this current flowing through this will decrease. So, if large current flows through this, current flowing through this is reduced. If less current flows through this, current through this is increased, such that the voltage at this point is maintained at say 10 volt. So, this can be maintained at any voltage as you like by varying this. So, by this way the current flowing through this produces now the fixed DC voltage. Now, all that we have to do is we have to convert this current, whatever that is flowing through that, anyway returns through this, and this current information will provide a signal. So, the signal to be obtained, to obtain a signal, what we do is we will add a resistance here. So, the current, entire current whatever is coming here actually flows through this. So, now this is our reference point 0 volt, and voltage at this point gives you the signal. So, that is V signal. So, the V signal is this R is known. So, this R into I is the V signal. So, we get this as 0. So, this is V signal which is equal to R into I. So, we will see how to use this to control temperature controller or some other system now, because this is another instrument which is used extensively in the field. So, next we see how to use this voltage, this regulated voltage and this signal to control the system that we are interested. Yeah, so far we have discussed about how to convert this current, this 420 milliampere current that is coming here into a regulated voltage, and then this gives you the voltage, the voltage across this is nothing but is proportional to the current that is flowing. So, we have now use this power supply regulated voltage and this signal to activate some process. So, first step would be convert this voltage, signal voltage into a usable positive voltage, because if you see carefully, voltage across this is negative, because this is our ground point and current is flowing like this. So, as current increases, you will have more and more negative voltage here. Say at 4 milliampere, for example, if I put here 100 ohms, at 4 milliampere I will get minus 0.4 volt, at 20 milliampere I will get minus 2 volt. So, the signal will be varying from minus 0.4 volt to minus 2 volt, then voltage, the power per power, the voltage will remain at 10 volt. So, now we have to convert this minus voltage into plus voltage, that we can do it like this. So, in the next what I do is I will take this 10 volt supply, I redraw this from this point. So, we have that capacitor here which is holding the voltage, and then this is the resistance which is having. So, this is our ground, and then this voltage is minus voltage, and we have here that operation amplifier and that resistance and so on, what we have discussed there. So, this is this, and then we have one more capacitor. We want to avoid the oscillation, we can use this. So, this is your 420 milliampere current. So, 420 milliampere current is here, and this is the resistance. Here we have 100 ohms. So, this is our ground. So, this first we convert into voltage, positive voltage, by applying this one to the minus terminal. So, we can do this, then I can have this voltage, and I can add this to this minus voltage, because the op-amp is working only on single supply, because we do not have the dual supply. So, we have to work this op-amp also in a single supply mode only. So, minus cannot be given to the input. So, input should see always positive voltage, and then the plus can be given to V reference, because here we have the V reference is there, we have the V reference at this point, which is given to this, and the output is compared here. So, this V reference voltage itself can be used for this purpose. So, take this voltage can be given here. So, if this is say 2.5 volt, and this also can be given some voltage, say 2.5 volt. So, if this is 0, if this is say minus 1 volt, then this is 2.5, you have 2.5. For simplicity, first what I do is I remove this. When I remove this, you are connected this 2.5 only to this. Oh, sorry. So, we have this 2.5 is connected to this. So, if this is 2.5, if this is minus 1, and we know this has to sit at plus 2.5, then we have 1.5 volt difference. So, this has to have 1.5 volt difference, that means this will go to 4 volt. So, at minus 1 it is plus 4 volt, then when it goes to minus 0.4, then you will have here minus 0.4. Then current is low. So, you have minus 0.4. So, you will get 2.9 volt difference. There is one small mistake. Actually, if we have earlier case, I just change this. Earlier case, assume we get minus 1 volt. Then the difference is 3.5 volt. So, we have to have 3.5 volt across this. That will give 3.5 plus 2.5. So, that is the output voltage will be 2.5 plus 3.5 volt. That is, assume this resistance and this resistance are equal. Then you have 3.5 volt difference across this. Then you will have 3.5 volt difference across this. So, that output will stay at 6 volt. This is for minus 1 volt input. For 0.4 minus 0.4 volt input, suppose if the input drops to minus 0.4, then output will be 2.5 plus the difference between these two. The difference between these two is 2.9. So, you will have 2.9, that will be 5.4 volt. That is V0. This is for minus 0.4 volt. So, as the current increases here, you find this voltage also increasing. This is that means, but this output voltage is positive. So, now we can use this to drive the some other device here, because now we got a signal which is positive, because what you have done is the signal at this point was negative, and we have no way of processing the negative because we do not have a negative power supply. So, we had used now the we have converted the negative voltage into positive by feeding it to this and keeping this one at 2.5 volt. Now, this can be used to provide whatever other functions that we want. For example, I want to operate an actuator depending upon this signal. For example, if it is 20 milliampere current in this, 20 milliampere current in this, you will have minus 2 volt at this point. So, correspondingly you will have minus 2 volt will give here actually 4.5 volt difference. 4.5 into 2 plus 2.5, you will get 7 volt at the output. So, we can use this one to operate some valve or some other temperature controller or whatever we want we can control. So, we take an example, that is assume that we want control actuator. then what we do is we will compare this output voltage with the reference voltage. So, if this reference is given to a positive, which can be this itself. So, I can have a reference, that is, this is our ground. So, I connect this to ground and then I can set this whatever value I want, and then this voltage, if it is very high, I can put a divider and suitably scale it down such that it matches with the reference. Then this can be used to for example, if it is a pneumatic actuator, then we use flopper nozzle mechanism to control the mechanical valve. In that case, flopper nozzle is operated using a very small current flowing through the coil. So, we have a coil, the current flowing through that produces a magnetic field that is enough to activate a small flopper nozzle, and eventually that will control the this thing, control the valve. Now, this also this is acting like a more like a on off controller. We can reduce the gain and make it a proportional controller by adding a difference amplifier to this. We can have a difference amplifier to this. Even this also can be done with this. So, you can have set the gain whatever that we want, and accordingly we can modify this as well little bit here to have the difference amplifier here. Even the gain in this can be varied such that you get enough voltage. If the voltage is not enough, this itself can be need not be connected here. This can be even connected to a high voltage supply, that is the mains voltage itself. So, that the difference between these two voltages will drive the current in the flopper nozzle mechanism, so that current flowing through this will be able to control the actuator. So, in this example we have designed a circuit starting from this 420 milliampere. So, what we have done is 420 milliampere current that is flowing here in this is converted into a regulated voltage. So, that is what we have done here. So, we got a regulated voltage across this point, say that is 10 volt. Now, then this is the one which gives you the signal, because this represents what is the total current is flowing. If they want the actuator to be at 50% level, they will be sending 12 milliampere current. Even at 12 milliampere you will have 10 volt, and then corresponding 12 milliampere you will have 1.2 volt minus 1.2 volt, that will be converted into plus, and then the difference between these two, it actually controls the actuator. If this current is more, then obviously the error voltage will be more, because we have set this one, and if the actually if the current is more, we want the actuator to move positive, then I can modify even this. For example, even we can do this way. So, if the okay, this got erased. So, you got this. We can connect if the more current, if you want more the actuator more, then I can give this one to the plus input, and then I can use this to V reference, or it can be also be connected to supply, or it can be divided and connected to supply. So, that you will get the difference between these two as a error, and the error will drive the actuator. So, so if the current is more, obviously you will have more error voltage, and the valve also will be moved more. So, this is an example I had shown you how to use this 420 milliampere current source such that you will get the power and the signal, and the signal can be used for whatever purpose that we need to have. Now, In this example, we had used a single power supply, and single power supply usage is very important in the process control industry, because normally we use dual supply for the op amp, like we put plus 15 and minus 15, and then we apply a voltage to plus terminal and minus terminal. For example, if I want amplifier, then I feed this and give the feedback to this output. Then in many times we may not have a dual supply, we have to work with a single supply only. That is what we have done in the previous example, like for example current transmitters and then voltage regulators and all these things, we are using only a single supply. Now if we are using op amp in single supply, certain precautions to be taken, that is, if we have a supply single supply like this, then plus I give the plus 15 and minus voltage I connect to ground. Then the operation amplifier have to work in a single supply mode. We have to make sure that input levels, for example in this case, suppose if I give the input like this, I give 0.1 volt per 741, and if I want to amplify like this, amplify say by a factor of 2, then I will have here for example R and R, then gain is 2. So you supposed you will expect 0.2 volt at the output, but actually if you do this for single supply with 741, you will not get 0.2. There is 0.1 into 2 gain supposed to come as 0.2. This will not happen for 741. Even LM324, which is meant for single supply operation, also gives some error. The point is that when you are using a single supply, we have to see for that what is the minimum acceptable voltage. For example, 741 will not work if you give below 2 volt in single supply, and output also will not go below 2 volt whatever you do. So if it is for example LM324, it works up to input goes up to 0.1 volt, output goes down up to 0.2 volt. So in all our examples, if you see, we never went the input terminals close to 0. We maintain always some voltage at the input, as well as at the output also we have to make sure certain minimum voltage is there, otherwise the circuit will not work. So for example in this case there will be some output voltage. If the output voltage, you do not want that output voltage, then we have to do one thing, we have to make sure that the extra voltage whatever is coming not driving this. One popular way of solving that is use put on Zener, so that minimum voltage whatever is coming from the op amp is dropped across this Zener. So this is one of the important observation we have to make in terms of usage of operation amplifier with single supply. So that is what we have done in this case. For example, many times if you want otherwise if you want to use a single supply, we can also make a floating ground, like say we have a plus supply alone is there, and then you have a ground. For example, if you want to amplify a very small voltage, they amplify through this, then you put on Zener diode here to the actual ground. This is the signal, then all your voltages can be amplified with respect to this ground. Then output also you measure with respect to this, whereas input supply is with respect to this ground. This is the true ground, that plus 15 volt ground. The output is between these 2 points, that is you will get your measurement signal is with respect to this. So we are artificially created on local ground. With respect to that, we are floating all our signals. This is one way of dealing with input output voltage limitation when you are using a single supply. So we had seen in the last 2 classes how to make a current transmitter to transmit the signal for a long distance. The current transmitters are used extensively in the industry to transmit the signal. As I said initially, this is to avoid the noise pickup, because magnetic field in the loop will not induce a will induce a voltage, but then the as long as the frequency response of the current transmitter is good, they will not respond for the magnetic field. So that is why the current transmitters are used. So we will see what are the different kinds of current sources are there and how they can be utilized for this purpose. So let us spend some time on constant current sources. So one of them we already seen one constant current source. For example, we have this is ground, this is plus 15. So current flowing through this, we have said earlier, this is Vz, this R is Vz by R. So this is a load. So current flowing through this load is always constant, that is given by this relation, and even if you change the load, this current will not change. Now this is one type of current source. There are very many different types are there, and each one will behave differently for different noise frequencies actually. Now to understand this phenomena, we should carefully look at the actual design of this circuit. If you see the actual design, we have the Vz across this, say 5 volt, we have assumed this is 5 volt, then if this is plus 15, then this is sitting at 10 volt. With respect to 0, then this is 10 volt and this is 15 volt. If this is 10 volt, then this also has to be 10 volt, because plus and minus terminals would be same. So if this is 10, then this also automatically comes 10, that makes the voltage across this is 5 volt. Suppose if this is not 10, because the current flowing through this determines what is the voltage. If this is 15 and if I put here say 100 ohms, then 50 milliampere current that is flowing through that will make 5 volt drop here, and that will be 10. Suppose if 50 milliampere not current is flowing, if more than 50 milliampere flows, then you will have more than 5 volt drop across this, more than 5 volt drop across this, then this will come less than 10. If this comes less than 10, then this is 10 and this is less than 10, then automatically output will go high and the difference between base emitter voltage will decrease, and that will make less current to flow. So then the current flowing through this will reduce. If the current flowing through this reduces, then voltage at this point will increase, because if this is 15 and voltage drop across this voltage minus voltage drop across this is only the voltage that you are getting here. So if less current flows, you will have less voltage drop. So this voltage will go towards 15. For example, 0 current flows, this is 15, this is also 15. As current increases, this voltage decreases. So current decreases means this voltage will increase. So if the current is low, then this voltage will be more than 10. In that case, this voltage will decrease, because this is more than 10, this is 10, this will decrease, then difference between base emitter will increase and you will have more current flowing here. So that way this will make sure that this is always sitting at 10. If this is 10, it is always sitting at 10, and the voltage drop across this will be equal to 5 volt, that is nothing but Zener voltage. So then assuming that this base current is small, then this entire current is flowing through this. So voltage across this, the current flowing through this, the current flowing through this will be Vz by R. That is what this current source is giving. Now if if I use this as a current transmitter, then what happens? For example, I do not put this, I connect this to a long distance and then put the load here and connect it back. Now the current is flowing like this. Now if there is a change in magnetic field in this loop, that will induce a voltage here, that will induce a voltage in this loop. This voltage it is a AC voltage, because that we know that BA n omega cos theta is the induced voltage, and here n is 1. So, the magnetic field is induced a voltage here, and this AC voltage will not drive any current through this, because if this voltage drives a current through this, that current have to come from the supply only, and that have to go, that current have to go through this. There is no way this current source can, this induced voltage can complete the path. If that current flows through that, then that will develop a AC voltage across this. If AC voltage is developed, then automatically this voltage will vary and correct it to make this current always constant, because AC current appears as a changing current, and the property of this current source is one make the current always constant. So, even if the AC current flows here, it automatically correct it and make sure that this only DC current is flowing, and if the load sees only DC current. So, this mechanically induced voltage has no effect on the load. This is the basic philosophy behind the use of current source to avoid the noise pickup. That is why in a process control industry they transmit the signal for a long distance using 4 to 20 milliampere current transmitters. We have different types of current source. We can see one more type of current source. For example, another celebrated current source is this. This is load, this I connect to plus 15 volt. Now, to make it a current source that depend on the voltage, what I do is I will pick up the voltage across this resistance. This is my sense resistance, this is the load. So, I pick up this voltage and apply it to inverting input, this I connect to ground. Then I pick up the voltage across this at this point, put a follower, then connect this one to this. This I connect to ground. Now, this had become a constant current source. Now, the current that is flowing through this I is actually, if this is V in divided by RS. That is, if I change the load resistance, the current through this will not change, that will remain constant, that is given by this. For this to happen, we have to design the values. Now, I will put the values. For example, I put here 100K, I will put this also 100K, I also put this 100K, this also 100K. So, I put here 100 ohms, here for example 1 volt. Now, if you analyze the circuit, see this is plus, if you analyze the circuit, whatever be the voltage here, that voltage actually coming here. Now, voltage at this point, whatever is there, is actually applied to the inverting input terminal. So, this is the external voltage that we are applying. Now, if you see, say if I write what is the voltage at this point, if I take this as V1 and if this is V2. Now, this is voltage at this point is actually V1 by 2, because you have V1 here, and that divided this resistance divides these two. You have one resistance here, one resistance here. It acts as a this output voltage is divided by 2. So, voltage at this point is actually given by V1 by 2. So, obviously voltage at this point also should be V1 by 2. So, this voltage also must be equal to V1 by 2. But then what is the voltage at this point? Because there are two contributions for the voltage at this point. One is from this input, another is from this point, voltage at this point. So, if current some current is flowing through this, then we will say voltage V2. So, what is the voltage V2 we can write? So, we can say V2 is V1 plus RS V1 minus V1 minus RS into I, because RS and I is the current that is flowing through this. I is the current that is flowing through this. So, voltage drop across this is RS into I. So, that means voltage at this point will be, this is V1. So, this is lower. So, lower by voltage drop across this, that is why we write V2 is nothing but V1 minus RS into I. So, this that means I can write this is voltage follower. So, this also equal to V1 minus RS into I. So, voltage at this point is V1 minus RS by Y, and voltage at this point is V1. So, we can write what is the voltage that we will get at this point. That will be half of this plus half of this. So, voltage at this point is V in, we can write in another way, V in by 2 plus this by 2, V1 by 2 minus RSI by 2. That is the voltage that you get at this point, because V in by 2 is at this contribution by this, then because of this half the contribution comes from here. So, this is this voltage is output is V1 minus RS by I. So, half of that. So, V1 by 2 minus RS by 2. So, voltage at this point is this, and voltage at this point voltage at this point is V1 by 2. So, V1 by 2 must be equal to this. So, I can equate this and then find out what is the current that will give us I equal to Vn by Rs. This I will I can do it in the next class. I can also explain you how this circuit works. So, eventually what we want to do is we want to show that V1 by 2, that is equal to V in by 2 plus V1 by 2 minus Rs into I by 2. So, actually you will get this and this getting cancelled. So, you will find Rs by I by 2 is equal to V in by 2. That makes it that will make it that will give Rs into I is equal to V in. So, that is why the current through that is I actually given by V in by Rs. So, that is why the current maintained constant. I will explain working of this more in the next class. Thank you.